So we'll start off with some relationships. If you can see this diagram here, you can see there's a right angled triangle with another one sat on top of it, such that they have edges or vertices here, here, and here. And as a result, we can ask ourselves what is the relationship between these angles added together and the difference between them. Now, one of the ones we're going to use, of course, will be cos A minus B. You'll see that. I think we've discussed that in the past, the usefulness of that with regards to complex numbers, and of course sine as well. So let's take a look at our first part. Our first conversation is going to be something along the lines of considering basic z. This can be seen here nice and neatly, if for want of a better phrase. Of course, we've got z is equal to r1 cos theta plus I sine theta, wherein this part here suggests the value along the imaginary axes, or the axes that can tend to be similar to the y-axis, and the cos here, of course, will be, or what else would be described as, this real part here, which or is often drawn as the x-axis. Now, given that z1 is equal to r1 cos theta plus I sine theta, this situation can itself, by the way, this is extremely poor handwriting and or a mistake in here, in that this should be a 1 or nothing. I think I'm going to go forward to call that a 1. As you can see here, when I then consider what z1 times z2 is, before I do that, let's put that in vector form. Let's say that this is here, this is going to be colored in such a way to be described as z. So this is going to be what my z is. So z1 will look like a vector, and I'm going to put it at something like that. Let's call that z1. z2 will make a slightly darker vector, z2 vector, in the way that it has some sort of direction, and we can call this length here its magnitude, but remember I'm talking about complex numbers, not vectors per se. So here it can be z2. And so when I do z2 times by z1, so if I do z2 times by z1, so these two multiplied by each other, again, this is the real axes here, also described by the value of cos theta, the value of it, and this is my imaginary axis described by the value of sine theta. Remember, this should be 1. So when I do that, it would be r1 cos theta 1 plus I sine theta 1 times by r2 cos theta 2 plus I sine theta 2. If I then do r1 times r2, so all I have done is to move this r2 to this point in here. If I was to do that, then I'd have them in the front, and I can start multiplying out this top part. So cos theta times cos theta, that's cos theta 1 times cos theta 2, of course. Then we'd have cos theta 1 times I sine theta 2. We'd have I sine theta 1 times cos theta 2, and I sine theta 1 times I sine theta 2. This produces cos theta 1 cos theta 2 plus I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2 minus sine theta sine theta. The last one manifests as a result, this part here, this minus I sine theta cos theta. Don't forget why that happens. That happens because I times I is going to be minus 1, and then sine theta 1 times sine theta 2 is what leads to that last bit there. So we have this situation here. Now, when you look at this, you can see that some of the double angle formula is starting to come out. You can see that you've got a multiple of causes and multiples of cos and sines and sines. If you go backwards here, you can see a multiple of causes, a multiple of sines, and so we can simplify this. To do that, though, and this is something that's universally important, especially in terms of exams involving complex numbers, what we're going to do is we're going to split into real and imaginary. That's what we're looking to do. And then we're going to use those trig rules. So here you can see I collect up the real, that's cos theta 1, cos theta 2 minus sine theta 1, sine theta 2. I collect those up nicely. So for example, you can see here where if I color this in such a manner, you might be able to see how I took it. Cos theta 1, cos theta 2. This is imaginary, it's got an I multiplied. This is imaginary, minus I sine theta 1, sine theta 2. So I just collected up the real there. To then collect up the imaginary, as I'll use yellow for this, I will simply do I cos theta 1 sine theta 2 plus I sine theta 1 cos theta 2. that is what I would do. And there is what produces this real and imaginary section there. The r's I've collected at the front, so technically there should be an additional bracket across here, something that can be put in if you are making notes, if you just to consider as we go through this conversation. So this should be all of this multiplied by r1, r2. Now the double angle formula here, let's use quite a dark red for this. You can see cos theta, cos minus sine. So you can see that cos minus sine AB is now theta 1, theta 2. So I'm going to utilize this relationship here to make a simplification, or to make things a little bit more simple. We've got cos theta 1 plus cos theta 2 instead. So that is how I was able to produce that. You can do the same for sine theta cos theta. So sine theta cos theta plus cos theta sine theta, and therefore this should be sine A plus B. So sine A plus B is there. So this simplification means that I can simply write this down as r1, r2 times by cos theta 1 plus cos theta 2, the addition of the angles, and sine theta 1 plus theta 2. So one thing to be aware of, if we consider that we originally just started off by multiplying our two vectors, then we can consider that when you're multiplying two vectors, so when these, well, again, I utilize the word vector, but really it is only in the sense that there is magnitude and a direction in terms of this Argand diagram. It is not a vector per se, but you've got your two complex numbers represented on this Argand diagram, and when they are multiplied together, then all you need to do is, as we've shown here, add the vectors. The only different, cos has not changed, sine has not changed, the thetas have been added together. And in terms of the lengths, the magnitudes, they are multiplied. So this is written in a manner as follows. It's written as, when you have these two, z1 and z2, multiplied in terms of r1 has to be multiplied by r2, then you simply just multiply them. The lengths multiply. It's very, very intuitive in that sense. But with regards to the args, which just means the angle, the arg, of course, being the angle from the x-axis round to the complex number, which maximum goes to 180 degrees or pi before having to be calculated negatively. Very aesthetically pleasing diagram there. So generally speaking, where are we? We are, when you see that the args are going to be multiplied, because you're literally multiplying the two together, which makes you imply that you're multiplying the angles from which that they describe. So when you're multiplying this by this, you are multiplying the lengths. We've already proven that. That is the Z1 and Z2. But also, you have to add the angle. So you add this angle in here. So there, you add that one, and you add it to this one here. Let's be clear, though, in terms of my diagram causing a little bit of issues. You have to add the angle of Z1, arg Z1, plus the arg Z2. So that is from the x-axis. This is what theta 1 and theta 2 represent. So we're going to use this situation to solve a couple of things, and also to find a pattern that's really powerful. The first thing to consider is z squared. We've just considered z squared because z squared can be described as z times z, which was, as shown earlier, simply this r here, very aesthetically pleasing. Let's utilize a better tool. Let's say this r cos theta plus I sine theta, and r cos theta plus I sine theta. Wherein we had a bit more detail last time, we said that this was theta 2, and this was theta 1, theta 1. Here I'm suggesting they're exactly the same. It's not z1 times z2, it's just z times itself. So I'm just using thetas, it's the same vector. So let's say, for example, I do the same diagram I showed you earlier. This is now going to be our lovely x-axis, which we can consider as real. So that's our real. And our imaginary is something like this. Let's pick a color to imply such a thing, something as colorful as pink. And then this z here is simply going to be something like, let's just pick there. And in so calling it z like that, What I'm saying is what happens when you do z times itself. So if you take z and you multiply it by itself, assuming that these are sat on top of each other. So z times z is just going to be r times r. The r's would be squared, so they'll be multiplied by themselves. So if the length was 4, it would be 16. The thetas we've already shown, we've proven this in the last part here, you just add the angles when you're doing multiple. So the cos thetas just come together as an add, and the sine thetas, their thetas, the thetas of sine, come together as an addition. So it'd be r squared cos 2 theta plus I sine 2 theta. Now what about z cubed? I'm not going to do z cubed personally. I judge it something that can be done quite easily relative to me reducing your engagement in this video by you having to watch me go through the same pattern. But what would happen is you'd have z1 times z2 times z3. You'd have 3 structures here to multiply through. You'll notice that you have a large number of causes and sines multiplied together. If you split into the real and imaginary and you do a little bit of algebra utilizing the trig rules, you will find that for z cubed you also have a lovely little pattern. The z cubed pattern will produce the same thing. It will produce z cubed equals r cubed cos 3 theta plus I sine 3 theta. And again, I would suggest trying to play with that one yourself. The practice for it is definitely worth it, considering that mathematics is about the number of times in which you've practiced a certain technique. Now, if z1 is equal to r cos theta plus I sine theta, and z2 is equal to r2 cos theta 2 plus I sine theta 2, then z1 times z2, you multiply the moduluses, and you add the angles. That's a little summary there. z1, z2, r1, r2, there's me multiplying, and there's the addition of angles. Now, when it comes to z squared, you simply would end up with r squared cos 2 theta plus I sine 2 theta. And when it comes to z cubed, you'd end up with r cubed cos 3 theta plus I sine 3 theta. And I would suggest you follow the same patterns in order to find that out.